Hello Math 1100 students. Let's begin Module 10, Rational Functions. A rational function is a function defined as a polynomial over polynomial, like this. Needless to say, the denominator should not be constantly 0, so not all the b values down here is 0. If they're all 0, then we have just constantly 0 denominators, so we have nothing. There should be at least one non-zero, and in particular we can select b0 as that non-zero quantity and take everything else as 0. Then what do you have? Let's make it even simpler. Let's take b0 as 1. Then what do you have? We have just 1 in denominator, so we just have the numerator. Consequently, any polynomial is a rational function, just like any integer is a rational number by taking the denominator 1. We are talking about a little bit more inclusive, a little bit more diverse category here. Okay, let's go to some examples. The first example, is this a rational function? A polynomial over polynomial? Yes, it is. How about this? That too, a polynomial over polynomial, so that's a rational function. How about this one? We have no x in there, but it's okay. It's a constant function. And is a constant function a rational function? The answer is yes. Any constant function is a polynomial function, and any polynomial is a rational function. Or you can just go back to the definition like this and name it as h of x. And let me expand the font. Okay. And take all the b values from b1 to bn, or 0, and take all the a values from a1 to am, or 0, and then you just have a0 over b0, and let's take it as 2 over 1. There you go. So any constant can be written as a rational function. Okay, how about this one? Let me copy and paste it and expand the font so that you can read this better. This is going to be a little bit more challenging because there's a bit of a problem in the numerator. Is this a rational function? A polynomial over polynomial? No problem in the denominator, you can clearly see that. The numerator may be a bit problematic because of this. So is that a polynomial? Yes or no? The answer is yes. This is not written in terms of polynomial over polynomial yet, but we can apply some algebraic manipulation and rewrite it in a correct fashion like this. Let me expand the font a little bit. So what did he do here? We just multiply the same quantity to both numerator and denominator. And what's that strategic quantity? Let's take x squared, so that's going to kill off this x to the negative second power. And then distribute and simplify, we get a polynomial over polynomial. This works for all kinds of negative powers actually. For example, let's define similar function like this and then add one more. 7x to the negative 10th power, for example. Okay, all right, as good as any. And is this a rational function? The answer is yes. Let me expand the font. Okay. All I have to do is to multiply a certain quantity both to numerator and to denominator. And what is that strategic quantity? You tell me. X to the what power? It's gonna be 10th power. So negative second power, negative 10th power, we have two terms to remove. And which is more negative? 10th power is more negative. So that's what you select. So distribute around. This is gonna kill off this. That's gonna kill off this one, and then 8x is to spare. So this will be a polynomial over polynomial. In short, it's okay to have any integer power. No matter how many negative powers you have, it's okay. You can select the power that is the most negative and then multiply that to both numerator and denominator, and then simplify. Now, if you have non-integer power, something like this, now you have a problem. That's not going to be a rational function. But whenever you have just integer powers all around, it's a rational function. Okay, we went through some elementary examples. Now the next topic is domain and range. Remember, we went through domain and range in, let's see, in chapter 3, in section 3.1, and also in 3.2. We went through all those. And in terms of my notebooks, it's lesson 5. And that was important. Please remind yourself of those. I told you that there were exactly 3 things to remember in college algebra level. Number 1, denominator should be non-zero. Inside of a radical, especially even radical, should be non-negative. And finally, inside of the logarithm should be strictly positive. Now, we didn't learn logarithm yet, so that's out for the time being. We don't have radicals yet, so that's also out. All we need to worry about is the denominator. And any domain problem is a big deal. In college algebra, domain problem is a big deal, and we're going to consider that thoroughly here. As for the range, that's out of scope. We need calculus, so we're not going to consider range problems for rational functions. For quadratic functions, we did consider range, yes. We had the vertex form and everything, but otherwise, no range. Okay, here we go. Plot a graph and determine its domain. Let's begin with the first problem. Ready, everyone? Okay, open up your grapher and graph it. Desmos graphing calculator is free for everybody, so please use it. Let's see. I already have it here, but in case you're wondering, go to any web browser and then go to Desmos graphing calculator or just graphing calculator, because graphing calculator, Desmos graphing calculator is popular, so it appears number 1. As a matter of fact, I made a typo, but still Google found out this Desmos graphing calculator, so let's use that. It's free, and Desmos also has free app, so please download it and install it to your phone. Okay, alright, let's go ahead. Y equals to the numerator 5x squared plus 3x minus 2 divided by the denominator x squared minus 4x plus 3. Did I type everything right? Okay, I typed okay. Alright, let's go to this graph and let's analyze it. Zoom out. That's the graph. What do you see? The predominant feature here is the horizontal line structure. It's not exactly a line, as a matter of fact. If you go closely in, it's curved. But in larger scale, it behaves kind of like a horizontal line and also kind of like a vertical line, even though they are not really vertical lines, as you can see if you zoom in. These kind of lines are called asymptotes. We're going to talk about those asymptotes a bit later, and that's going to be a little bit bigger issue for this entire module. But for now, let's stick to the domains. That's what we had been doing. Okay, we're going to talk about the asymptote a bit later. For now, domains. And I don't like this picture very much, so let me adjust the viewing window a little bit. Let's stretch it horizontally a little bit further, up to about this, -5 to +5. Okay, here we go. All right, zoom out. Yes, you can clearly see some, okay, you can clearly see that there are 3 curved pieces here. Does everybody agree? 3 curved pieces. 1, 2, 3. So let's go back to what we learned in chapter 3 or in module 5. 3 curved pieces. So the domain must consist of 3 intervals. Does everybody see that? Or does everybody recall that? Negative infinity to A, and then union, A to B, union, B to infinity. That's what we expect. 1, 2, 3 curved pieces. 1, 2, 3 intervals. And what are those A and B values? Let's go back to this graph. It looks like around x equals to 1 and around x equals to 3. We'll check. Now, one final question here. Bracket or parentheses? Of course, we have parentheses around negative infinity and positive infinity because infinities are not real numbers, so always that's going to be parentheses. Nothing is equal to infinity. How about A and B? Are they part of the domain or not? The answer is no. Look at the y-coordinate here. Y-coordinate is the function value, remember? I emphasized it many times since section 3.2. Now, y-coordinate is the function value, and the function value is being pushed away toward positive and negative infinity at x equals to 1. Same goes here. At x equals to 3, y-coordinate, the function value, is pushed away toward infinity or negative infinity. It does not stop. It cannot have well-defined y-coordinate value. If the graph abruptly stops, okay, that's bracket because we have y-coordinate. But pushed away all the way toward infinity, that's not a real number, so we cannot have bracket. X equals to 1 and x equals to 3, presumably, or at this moment, let's say A and B, those are not part of the domain, so they have to be open. So we have to have parentheses. We can get all those informations just by looking at the graph without going through any of these. Just look at the graph, and by the graph, we can make that educated guess about the domain. Okay? About this much, everybody should be able to do without looking at the algebraic expression of the function. Now, as for finding out what is A and what is B precisely and justify, you need to go back to this algebraic expression. How do you do that? Remember, denominator, radical, and logarithm, but 2 of them do not apply, just denominator only. So here we go. Set the denominator equal to 0. It's an easy quadratic equation. It's monic, so you can factor it and you can find x equals 1 and x equals to 3. And those are 2 x-coordinate values at which the denominator is 0. So at those 2x values, function value is not well defined, so they are out of the domain. Expunge those out, and what do we have? Those 2 numbers. Divide the number line in 3 pieces. We have 3 intervals. Just as expected. A and B values are 1 and 3 respectively. They are 1 and 3 respectively. Okay, that's a solution. And we went through the graphs as well. But just one more comment. This solution is okay. It works, but it's not the best way to handle it. The better solution here may be a little bit more time consuming, but I recommend it strongly. Work out the numerator and denominator simultaneously. In this particular problem, there was no interaction, so it was okay to do this. Just look at the denominator and work out. But who knows? There may be some harder problem where there's some interaction. In that case, you have to work out the numerator too. So this is what I suggest. Work out the numerator and denominator simultaneously, and then make sure there's no interaction. If there's interaction, then do something about it first, and then go to the denominator. That's how you can get the domain. Okay, so much for this problem, and looks like we'll have to resume our discussion in a separate video. See you soon.